Okay, let's talk about forces on ramps. Now, we're going to first of all talk about the constant velocity case that we've been talking about. Remember, there's two cases, rest or straight line cruise control. Just so you are familiar with that. We're going to start talking about that. Then we'll talk about what happens with an unbalanced. Well, if an object's sitting on the ramp, here's the key thing. If you're on a flat surface, Fg is equal to Fn virtually all the time. There are cases where it's not, but that's a special case. But usually it's that. Well, that's not the case as soon as you involve a ramp. As soon as you involve a ramp, now what happens? Fg is never equal to Fn, and we have to do a little trig to figure out what it is. So if I have a box sitting there, there's my ramp. Let's make it 30 degrees. Let's make it a common angle. Let's put a box on there. Now, let's draw a free body diagram of this box, and I'm going to tell you it's at rest. I'm going to tell you that point blank up front, so you need to know that because now you can solve it. Well, first of all, a free body diagram. If you want to draw a system schema, you can. I'll tell you what. Let's go ahead and draw a system schema. So we're familiar with it. We have our box. We have the ramp. We have the earth. So we're most concerned with the box. We know that the earth pulls on the box. We know that the ramp pushes on the box really in two ways. It pushes both as a reaction force, so there's a normal force, and also there's friction. Now, if you wanted to write friction as a separate thing, you could, but we'll go with that. So let's draw a free body diagram of that. Let's go down here and draw it. Now, key thing to understand, even though it's a ramp, Fg is still acting straight down towards the center of the earth, and that's really important. So Fg due to the earth. And as we've already talked about now, a normal force is a perpendicular reaction force from the surface, so it is perpendicular to the surface. That way. F normal, that comes from the ramp. Now, the fact that they told me it's at rest also gives me one more piece of information. The fact that those forces have to be balanced. What that means is there's a force acting that's going to oppose motion. Now, this object naturally is going to try and slide down the ramp, so therefore friction has to be directed up the ramp. Should be parallel to the ramp. So the force of friction, and that event again comes from the ramp. So that's our complete free body diagram. Okay, now that's not enough to solve anything. Of course, I didn't give you any information in this problem yet, but that's my generic picture. Now, here's kind of the neat thing that comes out of this is the fact that this angle right here turns out to be 30 degrees. It's based on congruent angles and yada 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 geometry stuff from years ago. But that angle actually turns out to be 30 degrees. So quite often to help solve these, I need something additional to it. Well, it's what I like to call a pseudo free body diagram. This is my free body diagram. This is what's going to be graded. This is what you need it to solve anything. You need to draw a pseudo free body diagram. Now, what a pseudo free body diagram does is it allows you to tilt the coordinate system, tilt the axis. It makes more sense in this system here to think about my x and y being like that. So that would be x, and that would be y. So what I'm going to do is tilt the coordinate system. I'm essentially going to do this and tilt the coordinate system to where it's flat. And the reason for that is now this point's in the y direction, in our new y direction, and this point's in our new x direction. This one has to be broken down into the part in the x and the part in the y. So let me go to a new sheet of paper and redraw that bigger so we can see what's going on here. So I'm going to come back to my original free body diagram. FG is going down. It's from the earth. FF is going up the hill. It's from the ramp. FN is coming this way. It's also from the ramp. And I told you that this was 30 degrees. It's important to understand that, because what happens with this, what happens with this case is this normal force is actually that it counteracts that part of the weight. So numerically, those are the same number. So this essentially becomes the normal force, but it's in the opposite direction. It's the part of weight that pushes into the ramp. So the part of the force that pushes into the ramp must be counteracted by the ramp. So this really becomes Fn numerically. Now here's the neat thing is, the part of the weight that's going down the ramp needs to be counteracted by this friction. So friction really becomes this side of the triangle. Now those are actually going to be the same length. Now my pseudo free body diagram is going to remove this FG and replace it with these. So in other words, let me redraw it over here, and I'll redraw it in red. This is my pseudo free body diagram, which is what I really need to solve the problem. What it's going to have is Fn going up. Again, that's from the ramp. It's going to have FF going this way. That's also from the ramp. But now, instead of drawing FG straight down, what I'm going to do now is draw I'm going to say F weight into the ramp. It's the weight pushing into the ramp. And over here, I'm going to draw this side, which I'm going to call the force down the ramp, because it's going down the ramp. Where did it come from? Well, it came from weight. And I guess I really should say this came from the weight of the object over here. Now, the nice thing about that is this has to equal that, and that has to equal that. If it's at rest, well, in reality, if it's at any type of constant velocity case, what's going to happen now is those have to be equal to each other. And that's kind of cool. Now, come back to this picture here, because now I have a right triangle. And if I have a right triangle, I can make some statements from that right triangle. I can say, so I'm going to call this side of the triangle F down. Let's call this side force perpendicular. And maybe that'll help us a little bit stay away from normal for just a minute. Now it's equal to the normal. So what I'm going to say is, well, if I look at my triangle, this becomes my hypotenuse. This side is adjacent to the angle. This side is opposite of the angle. So now I can use my trig functions to help me. So if I want to do opposite, I usually know the hypotenuse and I know the angle. Well, opposite of hypotenuse, according to SOHCAHTOA, was sine of theta is equal to opposite over hypotenuse. But in our case, it becomes the sine of 30 degrees is equal to F down, because that's opposite, divided by the total weight. And the total weight's usually given. So I can simplify that, and I can say, because usually I'm looking for F down, I can say F down is equal to FG times the sine of theta. That'll work all the time. Well, let's do the same thing with the perpendicular side. Now the perpendicular side turns out to be the adjacent, and adjacent in hypotenuse, so ca, that's cosine. So I say the cosine of 30 degrees is equal to F perpendicular divided by FG. Presto changeo, algebraic math stuff, and I get that the force perpendicular is equal to FG times the cosine of theta. So what that allows me to do is resolve it into its different parts. And of course, Ft is really Fn, is what it actually is. Numerically, it's in the opposite direction due to Newton's third law. Now, this algebraically gets a little bit sticky and all this stuff, and we'll do some practice with it to make sure that you're good on it. But at least allow it to sink in a little bit. I hope this helps some.